Hey, welcome back. In this episode, we're going to talk about recursion. So first up, what is recursion? And then we're going to dive into some examples of some really common computer science problems or functions that we would write with recursion. And we're going to do that in Ruby. So again, some more beginner Ruby stuff and talking about this concept of recursion. So what is recursion? If you Google recursion, you'll get this definition here, which is from the Oxford languages. It tells you that it is the repeated application of a recursive procedure or definition. And you're seeing like recursive here inside of the definition of recursion, and I don't know, like defining a word with the same word is like the definition of recursion. It's like a meta thing, like recursion and recursion. If you go down a little further, you'll see that Wikipedia has it defined as this, like, in computer science, recursion is a method of solving a problem where the solution depends on solutions to smaller instances of the same problem. So such problems can generally be solved by iteration, but it needs to identify and index the smaller instances at programming time. All right, so what does that actually mean? Who knows? Hard to say. But yeah, this is often referred to as like the divide and conquer approach to solving a problem, where like you are trying to break a problem down into smaller problems that look exactly the same. They're sort of the same shape. It's when a method usually calls itself, and as long as that method has one base case, it can break out. So there's a bunch of fun images on Google Images if you just search for recursion. So you get a bunch of these like funny, here we go again, here we go again, here we go again, all the way through. So that's like an example of recursion. Here's another example of recursion where you've got like triangles that are made up of smaller triangles that are made up of even smaller triangles that are made up of even smaller triangles, all the way down until you get like the smallest size triangle you can think of. There's also a bunch of other examples, like when you're kind of looking at yourself in a video editor and you see like yourself inside of the video, inside of the video, inside of the video a bunch of different times. That's another example of recursion. But at the end of the day, recursion is all about solving a smaller version of the same problem and kind of like adding on one layer. It's like a Russian doll, that Russian doll thing where you have like kind of a big doll and then you open it up and there's a smaller doll inside. Then you open that up and there's a smaller doll inside. And it's all like the process of opening the doll is like going to be the sort of the same action that you're going to mirror across all of the dolls as you work your way down the I don't know, shell of all of the Russian dolls. This video on YouTube, episode 6 or lecture 6, Recursion and Dictionaries from the MIT OpenCourseware, is excellent. There's a bunch of really awesome visualizations and stuff that this professor goes through. They use Python in this course, and he kind of goes through a little bit of the code, but doesn't go too deep in depth. So the content that we cover today will be sort of the Ruby version that is the actual live demo of some of the solutions to the problems that were presented in this episode. There's also a really cool visualization of Towers of Hanoi, which is shown both here on the side, and also that's this like Fisher-Price game where you have the towers and you try to move the rings from one tower to the other tower without ever putting a big ring on top of a smaller ring. And we'll talk about that process in just a bit. So that's what recursion is. Let's jump into some code. So I'm going to open up a new file here called recursion.rb. The other thing I wanted to do was like show how to write inline Rspec files. So I'm going to require Rspec here at the top. And in practice, if you wrote like a method called foo and you wanted to test it out, you could say like, oh, like puts foo, and then you'll see the output of foo. And then later on, if you want to write another method, then you would have to just like keep writing put statements or keep writing inspect statements to test your code as you go. But for these recursive methods, I wanted to write some tests for them. And so we can actually just require Rspec directly at the top of any old Ruby file. And then at the bottom, we can say rspec.describe recursion problems. And then we can actually just like start writing tests in here. So I'm going to say it works for a simple base case. And the very first exercise that I wanted to go through was implementing the code for the Fibonacci sequence. So the Fibonacci sequence is this sequence that looks like this: 0, 1, 1, 2, 3, 5, And can you see the pattern? At this point, if you're not familiar with the Fibonacci sequence, try to identify the pattern here. So we've got 0, 1, 1, 2, 3, 5, 8, 13, 24. This is like this is a sequence that's used in a lot of different things. I think it was originally developed by trying to figure out how many bunnies would exist in a box or something after they reproduce. And the example goes in more depth in that video for MIT. But this is a really famous sequence where each number is the sum of the previous two numbers. So 13 here is the sum of 5 plus 8. And if we look at 3, that is the sum of 1 plus 2. And 24 is the sum of 8 plus 13. That's actually not true. It's 21. Okay. So it's always like whatever the number is, it's like the sum of the previous two numbers. So what would be after 13, or I'm sorry, what would be after 21? Well, it's going to be the sum of 21 and 13. What is that, 34, I think, right? So we could go on forever and try to figure out what the Fibonacci sequence is, but we could also write a method to figure out these Fibonacci numbers. And this, like determining the nth Fibonacci number is a problem that lends itself really well to recursion. So let's look at how we might implement this. So let's make our method called fib of n, where we're going to pass in some number and it's going to give us back the nth Fibonacci number. So there's two steps that you need when you're writing a recursive function. First, you're going to need a base case, and the base case is going to be checking something about the input. And it's usually the base case is like the smallest possible case that you can look at, or maybe the first 2 or 3 or 4 possible cases. And then after you have your base case set up, then you're going to like actually recurse, or like call the same, like call myself basically, right? You're going to call the same method over with one smaller version of that same problem. So if we're looking at this problem, right, and we wanted to pass in some number, maybe we wanted to pass in 1, and we want it to give us back the number 1, or we wanted to pass in 5 or 6 or something, and it gives us back the number 5. So what we might do here is say that first we need to implement a base case. And the base cases in the case of Fibonacci sequence is if we get in a 0, so if we receive n is 1, maybe we want to return 0. So return 0 if n is equal to 1. So that's going to be like one base case. Then the next base case, we could say return 1 if n is equal to 2, because that's going to be this number here. And then we could also say return 1 if n is equal to 3, and return 2 if n is equal to 4, right? So at this point, we have like several base cases that are implemented. And we can actually, at this point also, maybe we'll just start with this. Works for a simple base case. So fib, expect fib of 1 to equal 0. And then here I'm going to say Rspec recursion, and that should run our Rspec test over here. And we see 1 example and 0 failure. So let's comment out our case there just so that we have a failure, because we want to start off with a red test. We want to start off with a failing test. We'll comment our base case back in, and we'll run this again. Okay, so it works for a simple base case. It works for a second base case, and we'll say expect fib of, let's say 2 equal 1. And then we will run this again. We'll run our Rspec test, and we see that we expected 1, but we got nil. That's because we haven't actually commented in our base case here. And we'll run this again. So now we have 2 examples that are working, right? And if we wanted to go even further and say that it works for a third base case, then we can say fib of 3 is also going to be 1. Okay, we'll run our test. And we get our failure, and then we comment in our base case. Then we run this test again, and so on and so forth, right? Okay, so we've got our base cases. Those all work. Now let's try a more complex base case, or a more complex case. So it works for a, let's say a complex case. And we'll pass in Fibonacci of, I don't know, 7. Okay, and so we have 1, 2, 3, 4, 5, 6, 7. So we expect it to give us back the number 8. So this is going to be the number 8. Now if we run our test, and it's going to fail. Okay, so what I'm going to do is I'm actually going to move these base cases up so that we can keep all of the test code on the page while we have, or I'm sorry, the implementation code on the page while we're looking at our tests, so that it makes it a little bit easier to follow. But in practice, I would kind of split these up a bit more. Okay, now we need to start on the process where we're calling ourselves. So in order to get the Fibonacci of n, recall that in order to find the next Fibonacci number, we can add the previous 2. And so Fibonacci of 7, or I'm sorry, of 7 here, right? 1, 2, 3, 4, 5, 6, 7. Fibonacci of 7 is the same as the sum of Fibonacci of 6 plus the Fibonacci of 5. So if we say fib of 6 plus the fib of 5, that should give us back our case down here for Fibonacci of 7, because it's the Fibonacci of the previous one and the one that's like before the previous one. So if we run this again, oh, we actually have stack level too deep. So shoot, my example did not work. All right, so let's actually say this is Fibonacci of 5. Sorry, Fibonacci of 5. So 1, 2, 3, 4, 5. So we're trying to find this number is 3. So we're going to say 3. And then here, the Fibonacci of 5 is going to be Fibonacci of 4 plus the Fibonacci of 3, right? So now if we run this again, we have a passing test. So that works for a more complex case. Now, we also want this to work for Fibonacci of 7, which should give us 8, right? Yes. Okay. So now at this point, right, like the way that we have written our tests, they sort of work for those base cases and they work for one complex case. But now we need to figure out, like, how do we derive 4 and 3? Instead of passing 4 and 3, we want to pass something else down to Fibonacci. So instead of 4 and 3, we can actually pass n minus 1. So if we're trying to figure out, the 7th Fibonacci number, then we want to pass 6, and we can figure out 6 based on, 7 minus 1. And then we also want to pass in 7 minus 2, and that's going to give us back the n minus 2 version. So now we are going to call Fibonacci with n minus 1 and Fibonacci with n minus 2 until we get to our base cases. So if we run this recursion again, now we have all of our examples passing. So this is going to work for both both of our base cases, all of our base cases, and a more complex case. Let's even like make this more, like, go out further. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th one should give us 34. Okay, so if we run this, all right, now we're still passing all of our tests. That is fantastic and looks great. So we have a working solution for finding the Fibonacci number, and it is this is using recursion because we are calling Fibonacci from inside of itself. Now, one thing that's important is that every single time that the Fibonacci function is called, the n is going to be associated with that function call. So it's going to be tied to that function call, and we're going to have frames. So every single time we have a method call, we're going to be pushing a frame onto the stack, which has reference to n. So when we call Fibonacci of n with some number, that's going to push a stack onto the frame with that n. So in the case of 4, we pushed on or I guess case of 5. So the other thing too is that, like, it turns out that we can actually figure out 2 based on the previous 2 numbers here, so 2 and 3. So we can actually just start removing some of these base cases and our code will continue to work, right? And furthermore, we can actually figure out 1 based on 0 and 1. So we actually don't even need that base case. So we can kind of like just keep going down further and further. And in fact, let's call that good. But like, yeah, there's ways that you can make it even fancier. Okay, so every time that you call the function, you're getting a new frame, and that frame is going to have reference to some number, and that number is going to be associated with the frame that's getting pushed onto the stack. So if we call this with Fibonacci of 4, then a new frame is going to be pushed onto the stack, and n is going to be equal to 4. And then as soon as we call Fibonacci here with n minus 1, we're going to be calling Fibonacci with 3. That's going to push another frame onto the stack. So we have Fibonacci of 3, and on that frame, n is going to be equal to 3. That's a separate frame from the one below it, which has n equals 4. So n equals 3 is going to be pushed onto the stack. Then as soon as we enter the function with n equals 3, we're going to get down to this call again. And when n is equal to 2, we're going to push another frame onto the stack. And then it's going to see that n equals 2 is here, and it's going to return 1. So that very first, or like that last frame that we pushed onto the stack where n was equal to 2, that's going to pop off the stack and return. And then we're going to have the return value here is going to be 1. We're going to have 1 plus, and then we're going to have to call n minus 2 again, and that's going to give us back 1. And that will return 0. And so 1 plus 0 is going to be returned from fib of 3. So it's a little bit tricky to follow, but keep in mind that every single time that we call the function, a brand new frame is being added to the stack, to the function call stack. And every single frame has reference to its own variables, or like its own like arguments here. So this is not, we're not using a closure here. Like this function is not closing over any other variables. Every single variable that we're accessing here was either passed in or defined inside of the function. We didn't actually define any in here, but the only reference that we're using that is like getting closed over is the reference to the fib function name itself. So that's the Fibonacci sequence. This is how you solve it. And this is a really common problem that you might solve with recursion. So also down in my Rspec method here, I want to say describe, and then I'm going to say fib, or just fib. And I'm going to put these into a describe block because I want to next go on to another recursive function called Factorial. So we're going to say describe fact. Okay. Factorial, finding the factorial of a number is another really common use case for using recursion. And so let's make a new method here called fact, and then talk about what the factorial is. So factorial is when you have some number, you might have like 5, bang. This is like a way to write the factorial function, is like the exclamation point at the end. And it means like if you have 5 bang or whatever, it means 5 times 4 times 3 times 2 times 1, all the way down, right? And so if you look at this, right, like 5 times 4 times 3 times 2 times 1 is really like whatever the number is times the factorial of the next lower number. So this is actually like, we can rewrite 5 factorial as 5 times 4 factorial, right? Because 4 factorial is going to be 4 times 3 times 2 times 1. And then like 4 factorial can be written as like, this one can be like 4 times 3 factorial, right? And so on and so forth. And so the smallest base case here is going to be 1. As soon as n gets down to 1, we just return 1. And then we're going to multiply that by the previous number. So let's try to implement this. So it works for a simple base case. And we're going to say like expect that factorial of 1 to equal 1. And we'll run our code. And it's failing because we are not returning anything yet. So we're going to say return 1 if n equals 1. The other thing that's worth mentioning here is that like I'm not handling invalid input. So if someone passes in -1, or if they pass in banana, or if they pass in some object, it's not going to work. It's going to crash. I'm assuming that like some validation, some input validation is happening before this, and we're just talking about recursion. All right, so the factorial of n, return 1 if n is 1, and then otherwise we want to return n, or so this is where we need to figure out like our recurse, right? So this is going to be our base case, and then we need to call myself. And so earlier when I made a bunch of base cases, right? When I was writing out, I wrote out all 4 base cases for the Fibonacci sequence. This can be a really helpful exercise when you're trying to just think through the model of what the pattern is for some sequence of numbers. And so in the case of factorial, right, like we could write, okay, return 2 if n is equal to 2, and then return like 6 if n is equal to 3. But it's a little bit harder in the case of factorial to sort of visualize it without going really far. Or the other way you could do this is like return 1 times 2, and then return 1 times 2 times 3. That might be like another way to sort of think about how we want to return from this function. Let's also add a couple more base cases here. So we're going to add like 2 and then 3. We expect this to be 2 and 6. And if we just run this, it should pass and it should totally work, right? Because we've written them all out as base cases. Now we can say it works for a more complex case. And here I'm just going to write like expect for to equal, what is that? 24? I think 6 times 4, 24. All right, so now we've got to figure out how to like actually call ourselves. So we know we're going to call fact of probably 1 smaller. Recall that like up here we were using like, oh, 5 factorial is the same as 5 times 4 factorial. So here we were passing in, if we were passing in 5, then it would be like call 5 times and then 4 factorial. So 4 factorial, here we have it written with an exclamation point, but really this exclamation point is the same as like the function call passing in n. So if we say factorial of n minus 1, this gives us 4 factorial. That gives us like, if we were passing in 5 as our number, this gives us 4 factorial, right? And so then we want to say like, okay, n times, right? Because that's going to give us the n times that number. And so if we now run, in fact, like this might even be an even better way to do this is like, what if we do like factorial of 1 times 2? And then we want to do like factorial of 1 times factorial of 2 times 3. That's like a better, even better way to visualize it, right? Like we have some number and then we have like the factorial of this 1 smaller times the number, or the factorial of 1 smaller times the factorial of 2 smaller times the number. So that sort of gives us the pattern. So now if we run our test, we have 5 passing examples. So we know this is working, and we can actually start removing some of these base cases. So if we run it now, it should continue to work. And I think we actually only need this one base case, return 1 if n is equal to 1. And then everything else should just sort of work. And it's so elegant, it's so beautiful, right? Just like 2 very simple statements, right? Return 1 if n is equal to 1, great. And then otherwise, return n times the next smaller case. And then we kind of like work our way all the way down. So that is factorial. I'm going to remove these from the base cases because, yeah. So let's also like come up with a more fun case. I guess factorial of 6. So what is that going to be? That's like 24 times 5. Oh gosh, 24 times 5 times 6 is going to be 720, I think. All right, let's run this. Okay, we have 5 passing examples, and that looks great. Okay, so we have now 2 examples of recursion that are really useful and tell you or show you how to like call a function from itself. Let's keep going. Let's do one more. We'll do Towers of Hanoi. So in the Towers of Hanoi, you have 3 towers, and on one tower it starts off with the disks in order of smallest to the biggest on the bottom, and your task is to move the disks from one tower to another tower, and the limitation is that you're not allowed to put a disk that is bigger on top of a disk that is smaller. So you can put any size smaller disk on top of a huge disk, but you can't put a big disk on top of a small disk. And you want to like move all of the disks over. And so there is like a small algorithm, which is like if you're trying to move all of the disks from tower 1 to tower 3, you're going to use tower 2, the tower that's in the middle, as like sort of your alternative tower. And you'll move maybe, if you start off with just 1 disk, right? That's going to be your base case. So you want to move 1 disk from some tower to some other tower. right? And so you can move directly. If you have one disk, you can move directly. If you have two disks, you need to move the smallest one first to the alternative tower, then the one that was underneath it to the big tower, and then the small one to the big tower on top of the bigger one. And then if you have three disks, then you need to move the small one to the big tower first, then the medium one to the middle tower, then the big one, then the small one back over to the medium tower or the middle tower, and then the big one to the final tower, then the small one back to the first tower, then the middle one to the final tower, then the small one to the final. There's visualizations online. Like go check it out. But the way that we're going to do it is that we're going to have our towers are going to be arrays. So we're going to have three different towers, and to keep it simple, we'll keep our arrays. We'll keep the representation of the disks as integers in the array. So let's describe, let's see, towers. It like moves it moves one disk, right? So this is going to be our smallest case. And so we need a from tower that's going to have one disk. We need a to tower that's going to start off as empty. And we need like an alt tower or like some temporary intermediate tower. And then we need a method to call. So we're going to expect that if we call towers, and then we're going to pass it the number of disks. We could just pass the from to an alternative. But in this case, let's pass the number of disks. So we'll pass 1 as the number of disks. Then we're going to pass the from, the to, and the alt tower. And actually, we don't want to like write expectation about the return value of that. We're going to have an expectation that like this one disk was moved to the to tower. So we're going to say expect that from to equal the empty array, and expect to equal 1, and expect alt to equal empty array. So we want the alternate after the end of this, the alt should be empty, the from should be empty, and to should have 1 inside of it. So let's run our tests. Okay, they are failing undefined method towers. So let's go make a method called towers, def towers, and it's going to take the number of disks, num disks. From, to, and alt. Okay, so if the number of disks is 1, then we want to move from the from tower to the to tower. So if num disks is equal to 1, then we want to like remove it from the end of the from tower. Also, like for reference, in the future, we're going to have our disks ordered like this, like 3, 2, 1. So like the biggest disk is going to be at the front and the smallest disk is going to be at the back. And so when there's one disk left, we want to remove it from the right side. We want to remove it from this side. So in Ruby, in a Ruby's array, we can call from.pop, and that will return the last element, and it will remove it from the array. And so then we can say to.push, and that will push it onto the end of, or like sort of the top of the stack for the to. Otherwise, we need to do our recursion. So like recurse. So this is going to be, this part is our base case. And I hope that this works. This should work, I think. Okay, we've got 6 passing tests. So it's able to move 1 disk, so that's great. Now let's try to get it to move 2 disks. So it moves 2 disks. So we're going to start off our from with 2, 1. And we want our to end up as 2, 1. And we need to pass in 2 disks. And we want our alternate to end up as an empty array. If we run this right now, it's going to fail because it's empty, because the number of disks was not 1. So in order to call myself here, we want to figure out what the smaller version of this is. So if we call towers again, we almost always are going to like call ourselves with one smaller version. So let's just say like num disks of -1. So that gives us like n-1 basically. Now the trick is when you are calling yourself, in the case of Towers of Hanoi, with the one smaller version, the location of the from, to, and alternate are going to change. So instead of passing from directly in here, I think we want to pass in, well, we still want to take off from the from, right? And we still want to put it somewhere. But in this case, I think the to is going to be the alt, and then the alternate is going to be the to. I know it's confusing, but let's just see if that works. Okay, so it did not work. We have a failure. We expected empty array to be in from, but we got the array of to. So, right. The other thing that can be helpful here is like every single time we get down to one disk, we can print out like moving disk from, and then we'll print out from to, and then we can print out to. And sometimes that can be helpful to see. So let's print it out as we go. And I don't see it. Num disks equals 1. I was expecting to see a little bit of output there. All right, so after we've called it with numdisks minus 1, we also need to ultimately get it down so that we're moving just one final disk from the from to the to and alt. And then again, we have to move. So like the base case is that you have some tower with n disks, and you move all of the disks that are on top of the smallest disk. You want to move all of those to your alternate position. Then you want to take, then your biggest disk at the bottom. Then you want to move all the disks that are smaller than the biggest disk to the alternate location. Then you want to take your biggest disk, move it to the final location. And then it's another problem of like, okay, now we have to take all the ones that were on the alternate location and move those to the final location. So we move all of the disks that are smaller than the biggest disk at the bottom from the from location to the alternate location. Then we're going to move our one bottom disk from the from to the to. Then we need to move all the disks again. So again, it's going to be numdisks minus 1 from the alternate location to the to location, with from being our new alternate location. So I think this might do the dance. Okay, so now we see our print statements coming out. So we're moving disk from 1 to, okay, so this is the more complex case where we have 2, right? So we're moving from the from tower that has 2 and 1 to an empty, and that's going to be the alt. Then we're going to move 2 to, so this is going to be our next case here. Now we're moving 2 from the from to the empty again. So now the empty is the ultimate final destination. This first empty is the alternate. The second empty is the final destination. And then we're getting down to our final call here where we're moving 1 from the alternate location to the final destination. All right, so I think we're at a place where we can say it moves like, I don't know, 5 disks or something. And we'll just say like 5, 4, 3, 2, 1. And we're going to be moving 5 disks. And we expect the 2 to have 5, 4, 3, 2, 1. And let's run this. Okay, so let's take a look at this output here. So it's a little bit hard to read, but we do start with 5, 4, 3, 2, 1, and we're moving it to the 2. What we want to do as we're looking at this output is ensure that they're always in descending order. All of the arrays are in descending order because our constraint is that we should never be able to put a bigger disk on top of a smaller disk. And so it looks like it's actually working totally as expected in that passes. So this is another example of recursion. We're solving Towers of Hanoi problem by sort of, we've got our base case and we've got these bigger cases. Now, I wanted to talk about one final piece, and that is how we can optimize for recursion. So if we go back to our first, or how we can optimize like not redoing the same math over and over when we've already solved that problem. So if we look at the case of Fibonacci, right? If you put in some Fibonacci number that is really large, like let's say even that we're going to do, I don't know, 1, 2, 3, 4, 5, 6. We're trying to figure out 5. In the process of figuring out 5, we're calling fib of n-1. So we're calling fib of 4. And when we figure out fib of 4, we're going to figure out, we're also calling fib of 3. So when we call fib of 4, that will also then ultimately call fib of 3. So we're going to end up calling fib of 3 like 6 or 7 times. But we only really need to call fib of 3 one time, because as soon as we know what the resulting value is for the Fibonacci of 3, we can just use that in all future calls, right? And so there's a couple different approaches to optimizing this. But one thing I wanted to do was add a brand new style of test called a timeout test. So we're going to say require timeout. This is another gem that you can use as part of your test suite. And I'm going to come down to our Fibonacci sequence thing and say like it is efficient, do end. And if we were to do like expect Fibonacci of like 100 or something to equal, I don't know what it's going to equal, so I'm just going to put in like garbage for now. I assume that the calculation is actually correct. But now if we run our tests, you'll see that it's pausing right here. Like the execution is stuck. It's hung because calculating the Fibonacci of 100 is doing those like fib of 3, fib of 3, fib of 3, fib of 3. Just like 1,000 times just trying to, or like way more than 1,000 times just trying to figure it out. So I'm going to cancel that. So that, I think that ran for 19 seconds. Let's see what some like decent upper bound is, like maybe 20. Does fib of 20 hang? Fib of 20, okay. So fib of 20 wasn't big enough. Fib of 40 maybe. There, fib of 40 is hanging for sure. Okay, so what we want to do is ensure that our tests are passing in. Okay, there we go. We got some number. Great. So let's use that as our result. Let's assume that's like correct. But the problem is that took 9 seconds. 9 seconds to figure out what the Fibonacci of 40 was. And that 9 seconds, like if you think about the Fibonacci, this method, or like you think about the calls to this method as like a tree, right? Like every time you call fib of a number, we have 2 new branches of the tree. So if we call with fib of 5, it's going to call a fib of 4 and fib of 3. And then if in fib of 4, it's going to call fib of 3 and fib of 2. And then fib of 3 is going to call fib of 2 and fib of 1. And fib of 2 is going to call fib of 1 and fib of 0. Like it's basically we're building up this giant tree. And we really only need to solve the very leftmost branches of the tree. And the rest of the tree, we've already figured out the answers to those questions. And so we need to like reuse those same answers. And so there is a term called caching or memoization. It's not memorization. You're not memorizing it. It's kind of like that. It's like basically the same thing. But memoization is when you're storing that result so that you can use it again later. So let's use this timeout library to write a little timeout thing down here. So we're going to say like, I think it's like timeout.timeout for 1 second. And we want to expect that a block runs and it doesn't raise an exception for, or raise error for timeout error. So we want this to not raise a timeout error when we call fib of 40. Well, actually, I think we can, I can't remember if we can keep both expectations in there, but let's just see. So timeout should actually time out after 1 second. Yeah, okay, so it timed out, I think, let's see. Using expect not to raise, risks false positives, yeah, I know. All right, so I don't care. So I'm gonna like suppress that warning by adding this one liner that's in the output. And then we see it hang and it fails because after 1 second it times out. So execution expired. So this timeout thing says like, if your test takes longer than or if like the block takes longer than 1 second, then raise an exception and fail. And so what we want to do now, the problem now is we need to increase the efficiency of Fibonacci or improve the efficiency of Fibonacci so that it can calculate the fib of 40 in less than a second. And the way that we're going to do that is with memoization. So we sort of need to keep track of previous answers, So if we have, there's a couple different ways we can do memoization or caching. The way that we're going to talk about today is by using a dictionary. So we're going to use a hash where the keys in the hash are n. So we're going to have some result, maybe we're going to have 3, and that's going to point at the answer for Fibonacci of 3. So 0, 1, 2, 3, so that should give us back 2. And then we're going to save the Fibonacci of 4, and that's going to give us back 0, 1, 2, 3, 4. So we only ever have to calculate it once, and then the next time, if we have already figured out the answer to that like smaller version, then we'll just return that. So the first thing we need to do is figure out how we're going to like pass in or reference or use this this memoization container or this hash or whatever. And so one way that I like to do this is I'm just going to pass in a dictionary here. This is going to be an argument that has a default value of an empty hash. And if we call Fibonacci with n and don't pass anything, it's just going to use this. If we pass Fibonacci of n with something, then it will use that the something that we pass in. So now what we want to do is we're going to continue passing memo forward for both of our other calls. And this is still going to fail. Like if we run the test now, it's still going to, like it shouldn't fail because we added an argument. It's going to fail because it's still slow. And so the next thing we need to do is actually speed it up. And so what we want to do is we want to say return memo at n if memo.hasKey n. So if it has the answer already, if it's already got the answer, then we want to return the answer. If it doesn't already have the answer, we do need to calculate the answer and then go down that branch of the tree. And we're going to store the result into memo. Memo of n is equal to the return value of fib of n minus 1, fib of n minus 2. All right, so now if we run this, we have a passing test. And that was like, boom, super fast, super fast. So it's running in like way less than a second to calculate fib of 40. And like we can even do like fib of 100 probably, and it will like just like no oh my gosh, like we don't know what the fib of 100 is. Well, I don't have it memorized, but like maybe some of you do. But now we should be able to run it, and it should like not just hang. Like it should just, now it's just eating it up, like no problem, because we're only calculating a super small sliver of the tree, and then we're reusing our answers, right? Also, just for fun, why don't we like print out p memo as we're like calculating it? I'm going to remove the put statements from towers just so that we can see it better. So, weird. I expected, oh, you know what? It needs to be after this. P memo. All right, so now we've got like all of our answers, right? So like this is the Fibonacci of 100. This is the Fibonacci of 98, 97, 96, 90, whatever. This expectation didn't actually run, but like the thing that we cared about was this outer one, not raising an error as we're running it. And so what's really cool is like you can see in our memo, right? 3 points at 1, 4 points at 2, 5 points at 3, 6 points at 5. You'll notice also that it does not include 0, 1, or 2, and that's because those are parts of the base cases, right? Cool. So this is how you might set up memoization and improve the speed of a recursive function. One thing to think about as you're trying to test these out and experiment with recursion, if you write a function that calls itself and you call it and there's no base case here, let me show you what error you're going to get. And you may have already seen this in your experience with writing Ruby. Okay, here we go. System stack error, stack level too deep. If you see stack level too deep, it's like 99.999% going to be the case that you have a recursive call that has no base case. Okay, so this is basically the same thing as a while loop, like a while true loop, with no way to break out of it. It is an infinite loop where instead of like just looping forever, you're going to recall that every single time we call the function, we're pushing something onto a stack. We're pushing a frame onto the stack. So every time we call f, we're pushing a frame onto the stack, frame onto the stack, frame onto the stack. And there's a check at some point where you're like 11,000 stacks deep in Ruby, where the stack level is going to be just too deep. It's not going to make any sense. And so instead of just infinitely running on forever and taking up all your memory, it pops and then just raises this exception that says, hey, the stack level is too deep. So you might see this error as you're experimenting with recursion. In this case, you'll have to just know that like there's a missing base case and it's not breaking out of the recursive calls at some point. So I think that's all I want to show. This is my thoughts and experience with recursion, a couple different solutions. We talked about Fibonacci Sequence, solving Factorial, Towers of Hanoi. There's a bunch of other really common use cases for recursion, like traversing a tree, especially like depth first search of trees and graphs and things. So I would really encourage you to check it out and experiment with recursion. That said, there are these really common use cases for recursion, make it really elegant solutions, but you can solve almost all or probably all the same problems that you can with recursion with iteration. So just looping, while loop, for loop, whatever. So this is just like another handy tool to have in your toolkit. Thank you again so much for watching, for your time and attention. If you're liking the content on the channel, I would love a thumbs up because that lets other people know that this is like good content. And yeah, if you'd like to see more Ruby or web development content, I would love to have you around. So hit that subscribe button. Thanks again, and we'll see you next time.